Hello everyone, thank you for being here today. My name is Jing from Shandong University. I'm excited to present our research here. The title of my paper is ArmVR Innovative Design Combining Virtual Reality Technology and Mechanical Equipment in Stroke Rehabilitation Therapy. This work was done together with my partners. Stroke is a significant global health challenge. It's the second leading cause of death and disability worldwide. By 2050, it's projected that there will be about 189.3 million years lived with disability from stroke. 17% of stroke patients have problems with their arms, making daily activities harder. Traditional therapy methods like repetitive strength training can make people lose interest, leading to low motivation and many drop-offs. This is where virtual reality technology shows its potential. VR creates interesting environments that can help with recovery, and using sights and sounds can improve motor skill learning. Given these challenges, our research goal is to develop ArmVR, a combined VR and mechanical system for personalized and game-like stroke recovery. We aim to address the limitations of traditional therapy by creating an effective rehabilitation experience. As shown in the figure below, A and B show the VR task interface. C is the parameter modification interface, and D, E, and F make up the overall system hardware components. To achieve this goal, we have three main research questions. First, does the integration of VR technology with rehabilitation hardware have a positive impact on rehabilitation therapy? Second, do different VR environments affect rehabilitation outcomes? In other words, do varying visual effects and auditory feedback influence users' perceptions during rehabilitation? Third, does using the same rehabilitation system yield different response outcomes across diverse groups? The ArmVR system includes a VR training system and a multi-axis manipulator. The VR training system includes a Meta Quest 2 headset and a motion feedback handle with FSR sensors. The multi-axis manipulator includes linear modules and a lighting platform. Data integration is achieved through fMirrors and pressure sensors, which provide comprehensive feedback on the user's brain activity and physical performance. The VR training system is a key part of ArmVR. The headset provides VR tasks. The handle is used to measure grip pressure and allows for rotation, supporting hand movements and matching the position of virtual balls in the VR environment. The computer interface lets managers change things like speed and how long a task lasts, and also watch real-time data. The software is built on the Unity 3D platform. The platform allows for the creation of adjustable VR tasks, such as those similar to the Pac-Man game. Collision detection triggers sound effects and visual feedback when Pac-Man collects virtual balls. Real-time communication ensures the VR task and the manipulator's movements happen at the same time. The multi-axis manipulator includes linear modules for movement on the XY axis and a lighting platform for adjustment on the Z-axis. It can be used by patients who are seated or standing. The control system is equipped with a microcontroller and safety features such as limit switches and an emergency stop button. The manipulator offers passive training at different levels: high, medium, and low. In our study, we involved two groups of participants: 24 healthy students and 12 stroke patients. The student environment includes 4 stages: resting state, task state in a forest environment, task state in a city environment, and task state without VR, each lasting 7 minutes. Taking into account the patient's physical conditions, the experiment was divided into 3 stages, each lasting 7 minutes: resting state, task state in a forest environment, and task state in a city environment. For data collection, we used apneas to measure brain activity. We used a particular pre-processing approach for the apneas data to deal with motion artifacts, and then we analyzed the brain signal complexity with multi-scale entropy. We also made use of pressure sensors to evaluate physical performance, working out metrics like peak, mean, standard deviation, range, and root mean square. Additionally, we collected subjective feedback through questionnaire, including the system usability scale, NASA task load index, and usefulness, satisfaction, and ease of use. For health users, we observed significant brain activation in the prefrontal cortex. In the forest environment, the left prefrontal cortex amplitude was higher compared to the control condition. In the city environment, the right prefrontal cortex amplitude was also higher. This indicates that VR enhances cognitive engagement, such as attention and memory. In terms of behavior, the city environment results in higher pressure peaks and a wider range of force output. In terms of subjective perception, users rated the forest environment higher in enjoyment and felt lower frustration in the forest environment. For stroke patients, the city environment showed higher right motor cortex amplitude, and the forest environment showed higher left motor cortex amplitude. In terms of behavior, the city environment resulted in higher standard deviation and root mean square. In terms of subjective perception, there were no significant differences in SUS and NASA and USC scores, but patients informally feedback that VR made therapy feel less repetitive. In conclusion, for RQ1, the combination of VR and hardware effectively enhanced motor cortex activation in patients and prefrontal engagement in health users. For RQ2, the design of the environment has a significant impact on outcomes. Forests help users relax with lower pressure and higher enjoyment, while city increases motor variability and cortical activation. For RQ3, the different responses from various groups showed the need for personalized rehabilitation approaches. These findings suggest that personalized VR environments can optimize therapy goals and the integration of apneas and pressure sensors provides holistic feedback. Future work will focus on longitudinal studies to track long-term recovery and AI-driven adaptive tasks for dynamic difficulty adjustment. Thank you for listening. If you have any questions or would like to discuss further, please refer to the email address provided in the presentation. for detailed communication.